Okay, so the big thing today, and this is sort of, the beginning of the rest of the course. So the first lecture towards exam 3, we're going to discuss something called power series. Now, I mean, come on, there's just something about that name that's just cool, right? A power series. How is this different from what we've been doing? Well, first and foremost, a power series is anything in the following form, and it's going to look a little bit different now. First of all, we start at n equals 0. Anything that can be written in this form. Now, you say, well, how is this different? Because we've already had the an, but now I have something here. If I expand this, I'm going to write the first few terms out. So when n is 0, I have a0, and I have this quantity raised to the 0th power, which of course would be 1. Then I'd have plus a1 x minus c to the first power plus a2 x minus c to the second, forever and ever and ever. So a power series by its definition is just a polynomial, but it's an infinite polynomial. It's a polynomial where there is no highest degree. So this translates exactly as this, but this notation is convenient. The an is the same thing it was before. Starting at n equals 0 allows, therefore, to be a constant term in the polynomial, because a polynomial, of course, you have your highest degree term usually all the way down to a constant term. Without the n equals 0, we'd be saying there's no possibility of a constant term. Now, the constant term could be 0. Most of the time it's not. And c is a constant that is either given or calculated before you do anything in the problem. We say that this power series is, the words we use, it's expanded about C. So it's kind of like C is in the center, and then I have this thing. So we're going to be doing a lot of examples over the next few days where we actually draw graphs of things. Now, here's the big picture. There's an infinite number of power series. You can just make one up. We'll make up some today, and then we'll analyze them and so on. Every function that exists, every function. Now, don't think polynomials. Think things like exponentials and sines and inverse trig. Think of things that are a little more complicated. It could be a square root. Every function that exists is equal to a power series. That's pretty powerful. Every function that exists is equal to a power series. One of our goals is to figure out what power series it equals. So the cosine of x is equal to a power series. We're going to figure out which one. So if I just make up a random power series, it's not equal to a specific function that we're worried about. No. But if I have a specific function, we will figure out how to create the power series that is unique to that function.
So it'd be like for natural logs,
there is
e to the power of x natural log. Okay.
Yeah, exactly. In fact, we're going to look at e to the x today. And we said, well, why would that be interesting? Because if I can show you that every function equals a polynomial, is there anything easier to differentiate or integrate than a polynomial? You can integrate or differentiate any polynomial. You can take limits of any polynomial rather easily. If every function is equal to an infinite polynomial, then if I had to integrate something, and I give you an integral that you can't integrate, but you could integrate the polynomial, that's a major thing we're going to look at. So this is the definition. So really the question is, next, if I have this, well, depending on what x is, this might be growing without bound. So it might not be a meaningful quantity. I have something that's just going off to infinity. So the first question we always ask with a power series is, where does it converge? Are there values of x that make this converge? For example, if x equals c, then this is the most boring power series. Because if x equals c, what is the value of this power series?
1. No, a of n, sorry.
0.
It'd just be,
doesn't it
That's what I meant,
converge
yes.
where x minus c is greater, or absolute value of x minus c is less than 1?
no, that's something else. Yeah. No, just I have x minus c in every term. By the way, you don't multiply this. You don't expand this. You don't worry about that. You're never going to expand this, because otherwise, what happens on the higher terms? If I replaced x with c, that'd be a very boring power series. because then it would just equal A0. But that's certainly a legal thing. What we're interested in is basically every other real number, okay? So our first goal today is to figure out, if I give you a power series, where will that series converge? Not does the series converge or diverge? No, all power series converge, period. I just showed you. If that's the power series and I replace X with C, I get a constant. That's kind of boring, but that's a finite value. Every power series will be finite for some values of X. We just want to figure out which ones. So let's start with something simple. Okay, let's start with something like this. I've got n equals 0, and I'm going to do, let's say, 1 over n squared times x minus 4 to the nth power. So, n squared plus 1. Sorry. 1 over n squared plus 1 times x minus 4 to the nth power. So if I just started writing out the terms to this, that wouldn't be very hard. You never need to write out the terms, but what does this actually look like? What are the first few terms? Well, let's see, when n is 0, I'd have 1 x minus 4th to the 0, that's just 1. When n is 1, I'd have 1 over 2 x minus 4th to the first power. If n were 2, then I'd have 1 over 5 x minus 4 to the second power. You know, it's going to go on forever and ever and ever. That's really, really exciting. But will this converge for every real number that I evaluate this at? Or maybe it only converges for a range of values. I don't know. So let's figure this out. How do I figure out where this converges? Well, we use the ratio test. Okay. On all power series, you use a ratio test to figure out where it converges. Why a ratio test? Because of that exponent.
Exponent.
I could use a root test, but you'll find the ratio test is easier in general. Plus, it will work no matter what the AN is. See, that guy might have factorials. That guy might be complicated. I can always use the ratio test. So our first goal is to take the limit as n goes to infinity. Now, what is the n plus first term? That would be 1 over n plus 1 squared plus 1. Remember, I replace n with n plus 1. X minus 4 to the n plus 1. And that I'm not going to do flip over. I'm going to just put straight over this guy. It'll be easier to read. Now, if I don't put absolute value, then any conclusion I make will be 100% incorrect. It's an absolute impossibility that I can get anything right if I don't have absolute value. Absolute value may be more important than getting the quotient right. Yeah. So before, when we were doing ratio tests, I said always put the absolute value, even though it really wasn't necessary back then. Now it's absolutely necessary because X could be bigger than 4, it could be smaller than 4. There's no rules. So now when I reduce this quantity here, I want to rewrite it in its simplest form. So the n squared plus 1 should go on top, obviously. And on the bottom, I'd have n plus 1 squared plus 1. And then I also have how many x minus 4s left over?
Just 1.
Just 1. Now, this quantity right here, the n's, this is strictly positive. That's not where the absolute value needs to be. The absolute value needs to be on this guy. So I can do this. I can make it so that's the only absolute value. Okay. Yes, of course, I can put it around the whole thing. But since that's a strictly positive quantity, so my answer is going to be the limit of this times the absolute value of x minus 4. That makes it a lot easier if I look at it from that point of view. Well, what is the limit of this?
Wait, how come we can factor out the x minus 4?
Because n is our variable for the limit.
Oh, okay.
Because it's a product, first of all. That's why we can factor it out. Right now, the absolute value goes over the whole thing, but only the x minus 4 could be negative. So I'm going to just have that in the absolute value. So I don't get mixed up. See, in other words, there's no limit for this term. The limit only applies here. So what is that limit right there?
Yeah, because of the variable, because we're taking the limit from n to infinity. Okay, I
Right,
got it.
not x, not x. We're taking limit of n, exactly.
Okay.
So what is that limit right now?
Just one.
Second degree polynomial, that's just one. So that means when I take the ratio of consecutive terms, I get just this. This is a ratio test. So what do I want to do with this quantity? Hint, hint. What do I want to compare it to?
1.
And I want to figure out, when is this less than 1? Everybody cool with that? When is this less than 1? Now, excuse me. An easy way of thinking about this, I want to go baby algebra here. I want all of the values of x, or all of the numbers, so that the distance between that number and 4 is smaller than 1. Does that make sense? I want the interval on the number line that kind of looks like that. And it's going to be easy enough to find because it's centered around 4. Oh, I'm going to go a little bit bigger than 4, maybe a little bit smaller than 4. I want this. Okay. Excuse me. My quantity is less than 1. Now, how do you remove the absolute value? You guys remember? That would mean that x minus
Plus
4
or minus.
between what and what? Between
1
what?
and negative 1.
Exactly. When I remove an absolute value, that's what we always do. Again, that's not calculus. That's like 9th grade algebra, but we sometimes forget because we haven't done it in a while. If the absolute value is less than 1, then the quantity is between -1 and 1. So how do I solve this? Well, add 4 to each term. So that would be 3 is less than x is less than 5. Now going back to my picture, doesn't that make sense? Yeah. All the numbers between 3 and 5 are within 1 unit of 4. Now you notice that is an open interval, isn't it? Because that inequality is strict. That's an open interval. So right now we have guaranteed that this quantity will converge for all real numbers between 3 and 5. That's not a very big interval, by the way. That's pretty narrow. Well, think about it logically. This is exponential in nature. So that kind of is going to dwarf the p-series-ish thing. So yeah, maybe it makes sense. Now, this is not a geometric series. I got this little thing in front. It acts like a geometric series, but it's not exactly a geometric series. We know that a geometric series does not converge when the ratio is equal to 1 or -1, right? It had to be less than 1 in absolute value. But because that's not a geometric series, it turns out it may be possible that this converges at either endpoint. Okay, so we found this first. Now what we're going to do is test the endpoints. Okay, so right now, here's what we have. So far, we have that this converges on the open interval from 3 to 5, which we generally would write this way. But now we're going to test to see if it converges at either x equal 3 or at x equal 5. Okay, so that's the next step. Excuse me. So it's a 2-step process. You always check both endpoints because there will always be 2 endpoints in this case. So we're going to test. Now, the question is, which one do you test first? Is there any advantage of testing one over the other? Yes. Whenever you have this kind of situation, one of the endpoints will cause this to alternate, the other one won't. You see, if I replace x with a 3, then won't
So
that
negative
become
negative
-1 to
one.
the nth power?
Alternating series. Yep.
Which means, by the way, every power series that exists at some point, you're going to get an alternating series. There's no way around it. Oh, okay. So which one should I test? The one that makes it alternating or the one that makes it not alternating? It doesn't matter, but if you want to save some time so you don't have to redo things, always start with the one that does not make it alternate. And I'll make that really, really clear. I'm going to start with x equal 5. Because if I replace x with a 5, then what do I get? Well, what's 5 minus 4? That's 1. What's 1 raised to the nth power?
1.
It's just 1. So all I have is this. Oh. Now at this point, we're going to kind of fast forward. Is this going to converge or diverge?
Converge.
1 plus 1 is going to
Converge.
you actually, this is one of the rare ones, you can actually do integral test, you could do direct comparison, or you can do limit comparison with 1 over n squared, which is a convergent P series. So we know this converges, okay? Converges. Now, when I test x equals 3, what's going to happen? We already said, what's going to happen? 3 minus 4 is -1. I'm going to get -1 to the n of n squared plus 1. Do I have to do any work whatsoever?
No, it converges absolutely.
Converges absolutely. That's why you test them in this order. If you test the non-alternating and it converges, the other one is going to converge absolutely always. Oh, so in other words, I don't have to do any work on the second one. It's an automatic, I can just say it. If this guy diverges, then this guy still may converge conditionally, but I won't know that until I figure out that this diverges. Does that make sense? So what do we got? We got that it converged at both endpoints. Therefore, the actual answer that I'm going to report, what notation am I going to use here, folks? It converged at both
Brackets.
brackets. That means it's a closed interval. Aha. So every number between 3 and 5, including 3 and 5, this thing will converge. Every number outside that interval, it will diverge. Therefore, we are not interested in any number outside that interval because divergence won't help us in any problem that we do. So a power series starts with a form. Second thing is we determine where it converges. Once we do that, we examine the endpoints to see the behavior. Okay, it's actually a fairly routine process, and it's going to kind of feel the same each time you do it. Okay, let's try another one. All right. Let's say we have something of the form. All righty. Throw a factorial in there because we haven't done many of those lately. We really like factorials, don't we? I think we do. I don't know. I do. Factorials, cool. All right, so we start by doing essentially the nth term test. Now, right now, this doesn't alternate or not alternate. It's just a power series. It can only alternate with certain values of x, which I don't know yet. So I treat this whole thing and I do the ratio test on that. So I'm going to take the limit as n goes to infinity. Now the n plus first term to n plus 1 factorial, x plus 1 to the n plus 1 over 2 to the n factorial, x plus 1 to the n, and then all in the absolute value. Now, am I going to get any canceling here? I'm going to do some scratch work off to the side. Okay. Can I write that as n plus 1 times n factorial?
Yes.
Yeah, I kind of need to do that. Now, let me flip this one up. I'm doing this off to the side so I don't lose myself. Do I get canceling? Yes.
Mm-hmm.
Any others?
Yes, the 2n times 2.
Mm-hmm.
So what does that leave me with? In terms of the coefficient part, 2 over n plus 1?
Yep.
How about this part here? Absolute value of x plus 1. Now, the reason I did the algebra off to the side is because it was a little cleaner. Now, there's nothing wrong with doing the algebra in here, but there's a tendency, all of us are guilty, that when we write over and I do all my canceling and stuff, you guys have never done it, right? You know,
Can I ask?
Wait, let me finish.
Sorry. You want you to finish first?
Let me finish. Yeah, I'm in the middle of the sentence.
Oh, okay. Okay.
Never write over your work and cancel because you will never be able to read what is left. How do I know? Because every person who does that ends up not being able to read what's left over. So take your time because I need this to be perfect. If I make a mistake, it will change my conclusion. Now, at this point here, when I take this limit, what is this limit going to be?
0.
0. I don't know, is that good or bad? And what are we comparing it to? We just did a ratio test, so what am I going to do now?
Since it's less than 1.
Less than 1. Now the question is, the first question on the first problem was, for what value of x is the ratio, the limit of the ratio less than 1? And we figured it was only between 3 and 5. For what value of or values of x is this ratio less than 1?
All real?
Yeah, the limit was 0. There's never going to be. So that means that x can be, say it again,
Means
All
anything-
real?
all reals. Ooh, that's not an interval. That's the whole real number line. So how do I say all reals? Converges for, because you always state your convergence as an interval. How do you say that?
All real. ALL. RE.
From negative infinity to
There's
infinity.
only one correct answer. There's only one.
Negative infinity to infinity.
Negative infinity to infinity. Yeah. That's all real numbers, but since our answers are always intervals. Now, Nicola, question, comment.
Oh, okay. So when you take out the so your very bottom work here, you take out the n+1 and the n on the bottom. How do those cancel out equally like that?
Well, let me do it with numbers, because it's always easier with numbers. If I have, 10 factorial over, we've done this before, over 9 factorial. Well, that's 10 minus
Wait,
7,
I
6,
think-
2, 1,
I
right?
think I understand. You canceled out the whole 2n on the bottom with a 2n on top, and then you'd have
I like what Tom said. This sometimes this makes it easier. How did you describe this, Tom? You didn't say it like I did it. You said it like what?
It's
2 times 2 to the n.
Does everybody agree that that's exactly the same thing? And so what
Yeah.
canceled was that with that. What we canceled was that with that. That's why these guys were left over. This is why it's a good idea sometimes to do your scratch work, and that's not a joke. Do it big enough that you can see what's taking place. When people write over and they're canceling left and right, factors get lost, not because you did anything wrong, but because you literally can't see it in the the chaos of crossing stuff out left and right. I like this, by the way, because then when I canceled the 2n, it was very obvious that there was a 2 left over. The biggest mistake is we got all of this right, but when we canceled, we may not have a 2 left over, that kind of thing. So this is a very interesting statement. So if I asked you in words, where does this power series converge? If you could give only one word, it'd be like a conjunction kind of word. It converges
Everywhere?
everywhere. Perfect answer. And by the way, that is our absolute favorite kind of power series. A power series that converges everywhere is a power series that has no restrictions. There's never going to be a value that gets us in trouble. There are power series that we're going to look at where the interval of convergence is so small that outside of that, crazy wild things happen, or worse, maybe at endpoints, it's a DNE kind of thing. We love it when it converges everywhere. You have no control over where it converges. Your job is just to discover where it converges. Once you write it down, the answer's set in stone, but this is the key right here. I take the limit. When is it less than 1? There will always be some place where I can do this, always. All right, let's keep going. And the steps that we're performing, I'm hoping feel somewhat familiar. The quiz you just turned in today is you're doing all of these types of steps. So let's try another one of these bad boys here. Let's suppose I've got something of the form, let's say n equals 0 to infinity, and I've got n+1 times, let's say n+1 times x to the nth power. Now, this looks different, doesn't it? What's different right off the bat about this one?
Well, I mean, there's no C. C is
There's no
zero.
Yeah, you don't have the x minus c format.
Therefore, what's C?
0.
0.
And by the way, that will be the most common value of C that you actually run across, a C of 0. Oh, okay. Nobody writes x minus 0 raised to a power. You just write x to the power. Therefore, it's of the form x minus C, where C is 0. So that's recognizing, oh, okay, the most common form. Now, part of the reason you're learning this is this becomes one of the most powerful tools to solve differential equations. Remember how we started the class? We did the separables and a few others. You're going to do much harder, higher level problems in a Math 255 course. One of the main ways of solving differential equations is to change the problem into power series and then solve the problem using power series. And in those cases, you'll always be using x to the n rather than x minus number to the end, just because it's convenient and it's the most common one. So let's examine this guy then. So the limit is x.
Professor,
yes.
before you start up on it, I want to apologize because we've been writing a lot. I might have missed it.
Oh,
We always do a ratio test.
for a power series, you can only do a ratio test.
Okay, thank
Just
you.
wait.
I'm sure you said it, but I just didn't.
Yeah. Now could you do a root test on some of them? You could do a root test, but you can't do a root test on all of them. The last example had a factorial.
Yep.
And so
Yeah,
because I can do a ratio test on every power series, but I can't do a root test on every power series, it's just recommended that you always use ratio tests. You don't think about it. Could you do root tests on some of them? Yes. But it turns out that the ratio tests, you're just going to find it's easier to be consistent because they always look exactly the same.
Thank you.
All right. So the n plus first term would be, what's the n plus first term?
n plus 1 plus
plus-
1 times.
So how
X.
about this? N plus 2?
Okay.
Let's keep it simple. Over n plus 1 x to the n. Well, that one doesn't look so bad, does it? That actually is kind of easy. So this is going to equal the limit as n goes to infinity of n plus 2 over n plus 1 times what?
Times X.
Times.
Absolute value of x.
He said, well, what's the difference?
Thank
If
you.
I do it times x, then there's not a closed interval. If you drop the absolute value, then it's always going to go from either negative infinity to number or number to positive infinity. There shouldn't be an infinity in your interval, probably. So the absolute value ensures I'll get it right. And once again, what does this equal? Well, this
1.
is exactly 1. So this equals what?
Just the
Absolute
absolute
value of X.
value of x.
No, sorry, I'll write the next time. This equals the absolute value of x, and I need to know when is that.
Less
Less
than
than
1.
That's not always true, is it? So that's true when x is in words between what and what?
-1 and 1.
Negative 1 and 1. So there is a very, very narrow window to where this is true. Okay, so now let's test our endpoints. So we're going to check x equal and x equal. Which one should we check first?
The plus 1, so
We'll check the positive one first. And that gives us, well, 1 to the nth power is just 1. Converge or diverge?
this looks simple.
Diverge.
It diverges because the terms are getting bigger.
Bigger.
Larger and larger.
That ends in the wrong place. It kind of needs to be in the denominator. Oh, so this, why will this diverge? Because it's going to fail what?
The
The
nth
nth
term
term
test.
test.
Well, the nth term test is, okay. So this diverges. It fails the nth term test. Therefore, do I need to test the other endpoint?
No.
No,
No.
yes. Yeah.
Because
Oh,
when you fail
divergence.
the nth term test, this is going to diverge to infinity. This is going to diverge without limit. That's the ugliest type of divergence. Remember I said last day, if you fail the nth term test, you fail no matter what type of thing you have. This fails the nth term test. This one will also, but even worse. So this already diverges because again, it's going to fail the nth term test. So now the final answer to this question is the open.
Diverges.
Well, the question is, where does it converge? It converges, sorry, it converges over the open interval from -1 to 1, which again, it's a very narrow interval. It doesn't converge for a lot of values, but it does converge somewhere. So we figure out, right? We solve the inequality, we test the endpoints. Very, very common theme.
Will
Professor,
we always get, sorry, you go first.
no, go ahead.
Will we always get rational numbers as opposed to like fractions for our range?
That's a great question. There's no always. It depends on the problem. I'm going to do a few more because I want you to see as many different looks as you can. So you don't want to be predisposed to saying, I think the answer is going to look like this too far ahead of time, because the algebra here, this is really all of it right here, isn't it? It's just not that complicated. So
Professor, when do we get a conditionally converge conditionally?
well, I'm glad you asked.
Well, before you continue with it, then I also have a question about this one. If it does converge at either x equals -1 or 1, does that, the only thing that means is that when we're talking about where the answers matter, it would just be a square bracket compared to a, cool, perfect.
These are your 4 options.
Just making sure.
By the way, that's the right question. We just haven't seen does everyone understand that once I got here, these were the 4 possibilities. Fails at both, successful at both, successful at the left, or successful at the right. Does that make sense? Those were my 4 options. I don't know what they are until I test the endpoints, but all of those were possibilities. So the conditionally convergent would be one that looks like this one.
I don't, is the bottom right one even a possibility? Because if it converges for n equals 1, doesn't it automatically pass?
Well, no, I'm just saying, I'm saying in general, when you're answering a question and you have this, there are 4 possibilities of brackets and parentheses, and you're going, but wouldn't it automate? Well, you don't know which one made it alternate though. Careful. It could be the other one. If you're assuming it's always one of them versus the other, that's not necessarily the case. Yeah. All right, so let's do, somebody wants to do a conditionally convergent one. We just really want to conditionally converge. All right, so let's do a simple one. All of these, I'm hoping in the end up being what you would deem, as a simple one. Let's suppose we have 1 over 4 to the n times n plus 1. And over here we have x plus 2 to the nth power. This is not complicated in any way. This is about as generic as it gets, but we can't jump the gun. We can't try to go right to the final answer because we'd be maybe missing some pieces. So we start like we did each problem so far. All right, so 1 over 4 to the n plus 1. If I replace n with n plus 1, of course, that becomes n plus 2. This becomes x plus 2 raised to the n plus first power. Then I'll just repeat that thing. All right. Well, clearly there'll be some canceling. How much canceling will I get here? I probably can fit it right here. No, I'll put it over there. It's a little too tight. Now, that n plus 1, definitely have that. What about the 4s?
Just going to be 1 over 4.
Yeah, basically that's what I was going to ask you. Is the 4 ending up on top or on the bottom? Well, there are more 4s on the bottom, so this is going to be 1 over 4. How about if I just put it right there? Can I do that? Is that legal? And then what's left? Absolute value of x plus 2. So when I stare at that, make sure, right, the n plus 1, if you flip this over, okay, 1, 4 on the bottom, beautiful. What does that limit equal? Well, what does this part equal?
1 over 4.
1 over 4. So this equals 1/4 x plus 2. And I'd like to know when that is less than 1. So what do you suppose I should do next? Should I remove the absolute value?
Factor out the 4 or the 1/4 first.
Factor it out. Well, it is factored out.
Times
Or
4.
sorry,
How about just get rid of it altogether?
yeah.
Yeah, you
How do
multiply,
you get rid of it altogether?
multiply by 4
Is that legal?
Yeah.
Is an inequality? Is that legal?
if
Yes.
it's not negative.
Because it's not negative. Good. That's the
And
right.
if it's negative, can you just flip the sign?
Flip the sign. I'm not sure what that means. You have an
I mean,
inequality.
If you multiply an inequality,
If you find yourself multiplying it by a negative at any point, it means we probably made a mistake because it was an absolute value.
Okay, well, in general, in algebra, if you multiply
The
by
rule in
negative,
algebra is if you multiply both sides of an inequality by a positive number, you preserve the inequality. If you multiply both sides of an inequality by a negative value, you change the direction of the inequality.
that's what I
You
meant.
don't change the sign, you change the inequality. Yeah.
Oh yeah, I did say sign. I meant the
Well, I know,
inequality.
I know what you meant. I'm a minor here. So this is less than,
4.
4. Now, up till now, all the examples we had done, it was, for most part, it was less than 1. Now I got something that's less than 4. So if I drew my number line now, first of all, where is this centered about? I want you to have a simple visual. Where's the center? X plus 2, is it centered at 2?
-2.
Centered at -2, because it's x minus -2. But this means I'm going to go 4 units in each direction. So this number right here, the 4, this is called the radius of convergence. And that word should make perfect sense. It's radius. You think of how far do you go in each direction, like, in a circle. From the center, the radius is how far you go to each edge of the circle. The radius of convergence, my absolute value is going to be smaller than a number. That's the number that basically I'm going to add and subtract at some point. I'm going to be moving 4 units in each direction from -2. So my radius, that distance is 4. In the previous examples, most of them, the radius was 1. But I didn't have reason to define it until now. So now when I remove the inequality, isn't it true that this will be -4 is smaller than x plus 2 is smaller than +4? Now, if I throw a -2 on each term, I'd have -6 is smaller than x is smaller than +2. And that's our -2 adding and subtracting 4. So right now at this point of the game, I can say, I know it converges. And by the way, we don't do this next step, we don't do in permanent marker, by the way. Everybody understand what I'm saying there? I don't do that in permanent marker because now I have to test the endpoints. Either of those can change. Either one of these can change the closed brackets. Okay, they both may remain open, they both be closed, or one of them. I don't know until I test the endpoints. My endpoints are this number and this number. So based on, can I get this in there? Yeah, I think I might be able to get this in there. So which one do we want to test first?
2.
I want to test the 2 first. So at x equal 2, I will have what? I know this is a little bit cramped here. When I replace x with a 2, I'm going to have a 4 to the n. So I have 4 to the n on top. 4 to the n plus 1 on bottom. That's just 1 over n plus 1, isn't it? Everybody cool with that? Now tell me about that series. Does that converge or diverge?
That
What does it look
Diverges.
like? It
Which
looks
is-
like a harmonic series, doesn't it?
Yeah, diverges.
So that one's going to diverge. I'm going to have to finish somewhere else. Okay, this diverges.
Do we have to go about proving that it's diverging via the normal method that we've been doing the last
Well,
week, or can we just?
yeah, yes and no. You can say this is a harmonic series. Remember things of that form. It is a harmonic series. You don't have to test a harmonic series. It is harmonic. Remember what is a harmonic series? Oh, the 1, 1/2, 1/3. This is a harmonic series that starts with the second term. It's, remember, it's not the harmonic series. If it makes it easier to think about this, this is the same as 1 over n
Mhm.
starting at 2. Does that make sense?
Yeah.
Oh, okay. So you don't have to prove it. You can just say it. It's a divergent harmonic series. And here's,
I only asked because, previously we were doing, 1 over n squared plus 1 compared to 1 over n squared. to
yeah,
prove
I
that-
was just saving some time right now. But yes, generally you would still do your tests, but the tests are trivial at this point because what you have left have been like simple P series kind of stuff. So those tests will be like light speed, which is good, because the problem now is a new thing. The problem now is, tell me about X, because you've practiced how to determine convergence and divergence for things that look like that. Now, tell me about, I'm gonna erase this. Tell me about the next one down. The next one's critical. Now we're gonna test that endpoint. So at X equal -6, take your time. If you go too fast, we might make a mistake because now I've got more stuff going on. When I put a -6 in there, what do I get?
-4 to the n.
Can I, that's something, I don't like the way that feels. I don't
So
know.
you-
That doesn't give me warm fuzzies. Let me remind you of something though. True or false?
True.
Always true.
To take the
-1
1.
to the n.
Oops, sorry, I put that. -4.
As you're spoiling it.
Could I write it like this? Is that legal?
Yes.
Yes.
I'll allow it.
That's how we're going to do it. So although I can't cancel, because if I do, I'll just get the value -1. Oh, I'm going to cancel the 4 to the n, but that's going to leave me with a -1 to the nth power. Because we were expecting this to alternate, weren't we? So now it's -1 to the n over n plus 1. Will this pass the nth term test?
Yes.
The non-alternating, well, yeah, I can look at this guy. This guy's going to pass the nth term test. Therefore, this one converges.
Conditionally.
Beautiful. You asked, I provided. So I'm going to abbreviate because I'm running out of space. So this guy converged. Now, someone said it and you were correct, but it's not an absolute. If you're only going to converge at one of the endpoints, it can only be the alternating. You cannot converge at the non-alternating and then diverge at the alternating, because if you converge at the non-alternating, you converge absolutely at the alternating. If you diverge at the non-alternating, you can converge at the alternating conditionally. So if you only converge at one, it's the alternating. I said, so that thought process was correct. I said, the danger is don't assume that it's always the smaller number that's alternating. No. It's easy for me to construct a problem where the bigger number causes it to alternate. It doesn't take much tweakage to make things different. So you still test, but always test the non-alternating first, and then the alternating is where you get the conditional. So how does my answer change? It has to change now because of that. So how does it change?
The
So-
square bracket on the -6.
I'm a -6. Beautiful. And that is why I said don't do this in permanent marker. We knew the -6 to 2. We just didn't know if it was going to converge at the endpoints. Okay. You can't know if it's going to converge. You got to test it. But the test for convergence at the endpoints is essentially what we've been doing for the last week, testing simple series. So right now we don't have any use for the power series. I don't have an application yet. Oh, there's tons of applications. If you've actually looked at the posted notes, if you look later on in the notes, you see the word application. You see application quite a few times because there are so many different versions of applications. So we got to get the basics first, then we'll look at applications because applications are cool.
Professor, I have a question.
Yes. Before I erase?
It doesn't really matter.
Okay.
Remember before when we were doing the alternating series,
Mhm.
and we get the alternating series, which is in the form of a -1 to the n power, and then you would say consider this integral, which doesn't have the -1 to the nth power.
Yes.
When we're doing these power problems, if we choose the non-alternating number that does that first. Is that always going to be
The consider part?
the consider part? Yeah.
Absolutely. Oh, no,
Okay.
no pun intended. I absolutely probably is the wrong word. Yes, the answer is yes. That's why I'm
Okay.
pointing to this
That's
one.
cool.
Oh, that's why I didn't have to write out a whole proof of this. I got it sitting right there. This is
Right.
the non-alternate. This is the one that, and those are the perfect choice of words, by the way. This is the one I would have written, consider this, but I can easily look at that and say the limit of this is going to be 0. Okay, passes the nth term test. It's alternating conditional convergence. You don't have to do a whole lot more. And let's face it, you don't want to have to do it. You just want to get an answer. Now, consider the following series. I want you to consider this one right here. This one is very, very interesting. Okay, my ends are pretty awful looking. I want to mess around because technically this is a polynomial. We know that the limit of a sum is the sum of the limits. That was the very first limit property we proved. We know that the derivative of a sum is the sum of derivatives. We know that the integral of a sum is the sum of the integrals. That summation applies across the board. So does scalar multiples. So I want to consider the derivative of this guy here. But how do you take the derivative of a power series? Well, first thing you do is just let's write out the first few terms. That's the easiest way to analyze this. So let me write out the first maybe 4 or 5 terms of this power series. Okay. So when n is 0, well, what's 0 factorial again?
1.
0 factorial is 1. So I'd have 0 factorial x to the 0. Okay, the first term is 1. Plus 1 over 1 factorial x to the first, plus 1 over 2 factorial x to the second, 1 over 3 factorial x to the third. I'll just go this far. 4 factorial x to the fourth, plus, okay. Forever and ever and ever and ever and ever. We all agree with that? I can definitely simplify. You usually don't leave the factorial in the answer because you can simplify. Well, what if I don't know how to simplify? Then you use one of these. but don't leave the answer as 1 over 4 factorial, write the actual fraction. So this would be 1 plus x plus a half x squared plus a 6th x cubed plus 1 over 24 x to the fourth, on and on forever and ever. All right. Now I would like to take the derivative of this. Now, to make my life easier, let me go ahead. I'm going to rename this. I didn't read myself enough. I'm going to call this f of x. Let's just call this f of x. We can do that for every power series that exists. We can just call it a function because it is. So what I wanted, oh, we got a cool echo there. I want f prime of x. I don't know how to differentiate that. So let's differentiate that. Okay. Everybody cool with that? Let's just differentiate the second thing. So if I differentiate all of this, what am I going to get? 0.
1, 2.
Okay, well, careful. Not 2.
Oh, I'm sorry. 1.
1x to the first. Okay.
So 1 half x
squared.
1 half x squared. Okay.
1/4 x cubed.
1
1/6.
1/6 x cubed.
6x cubed. Okay. And okay. All right, cool. Does anybody notice anything? This is f
the
of x.
same power series.
F prime of x, and it's exactly the same thing.
So is it E then?
Well, that is the question. I just made up a power series for fun. I just made this up off the top of my head. Never seen it before in my whole life. I took the derivative and I got the same thing. Yet in mathematics, of the infinitely many functions you can write, there's only one. And there is only one.
I think we're done for the day.
There's only one function that equals its own derivative. This is an absolute mathematical
E
statement.
to the x.
So that means that this must be e to the x. Whoa. Now, I'm telling you, I'm not deriving it yet. That comes in the future. I don't have my syllabus in front of me. That's either tomorrow or the next day or something like that. We're going to derive it soon enough. But the fact is, I just showed you, I didn't tell you, I just showed you that e to the x is equal. Now that is the crazy part. It's equal to this. But e to the x is called a transcendental function. Transcendental functions that are not polynomial based and algebraic functions are not transcendental. I took a transcendental function, e to the x, and I said it is equal to a polynomial. Now, nothing could be crazier than that statement. So how can we possibly make such a bold statement? Oh, by the way, where is this being expanded about?
X.
It's a scalar. Where is it being expanded about?
Oh,
0.
not really understanding the question.
0.
0.
X minus c is the form of a power series, and we said it's expanded about the c. Oh, this is expanded about x, which means that x equals 0 or c equals 0. It's kind of like the center. So hold on a minute. I'm going to do something kind of cool on my calculator. I'm going to write out just the first few terms. I'm going to write out just this many terms on my graphing calculator. Okay, just give me a second. So 1 plus x plus hold on a second. Lost it. There we go. X squared over 2. There we go. Okay, I'm just going to do the first few terms. I'm not going to do tons of terms. Plus x problem. The light in here is not great. All right, plus okay, now I'm gonna do my window. Let's say we're gonna go from, I'll go -10 to 10. Well, no, not -10. Let's say negative. Yeah, we'll go -10 to 10 in each direction. Okay, that's always a good starting point.
It kind of matches up with the, I don't want to say in Steal Your Thunder, but
Okay, now let me go ahead and graph it. I just want -10 to 10 in each direction. Is anything gonna happen here? There we go. Okay, I just want -10 to 10 in each direction. Okay, we said, well, that kind of looks like a parabola-ish thing. You're right. So
well, no,
remember I said close to 0. So let me change the x from -10 to 10. Let me change the x from maybe -5 to 5. Okay, let me zero in on, whoops. Oh, hold on a second. That didn't like that last command. Okay, -5. Whoops, why is it not letting me do that? Expand. Oh, here we go. All right, -5 to 5. Okay, I'm going to change the just slightly. I'm going to bring in the x just a little bit. Okay. And the same thing is happening. I'm getting this bigger window. So let me zero in one more time. This time, let me just go -2 to 2. You're going to like this. Okay, -2. I could make it obviously a bigger window, but I want you to be able to see what's going on. Now I'm going -2 to 2. Okay. And so you see something happening here. You're going, yeah, that graph looks vaguely familiar. Okay.
x.
Okay, now here's what I want to do. I want to now also, on a different set of axes, I want to actually graph e to the x. If I can find it on here. Hold on. Where's my, there we go. E to the x. Now I'm going to do a second graph. Whoops, hold on, enter. There we go. Now I'm going to do a second graph. Now there's a second graph being produced right now. Can everyone see it? Can you all see my second graph? Well, you can't really see my second graph because it's so darn close to my first graph. So let me back out again. Let me back out what we did before. Let me go -5 to 5 again. I think it'll be more obvious. I'm giving you a little insight on the nature of things. Okay, so the one that's coming down from on high and then go, That was the first graph we did, but remember we zeroed in on it. Now the second graph should be showing up in a moment. Now you guys see something there? There are two graphs here. But the second graph is right along the x-axis, then comes up. So in everything pretty much from the y-axis over, and really from about -1 or -2 over, can you see a clear difference? Or do they basically look the same? Because there are two graphs there. Do they basically look the same? Yeah. The point being, I said e to the x is equal to this infinite sum, but when I just drew the first few terms, e to the x looked like the first few terms. Well, it isn't exactly the same, it's asymptotic. Remember that term? E to the x is asymptotic to this simple polynomial. It's equal to the infinite polynomial. It's asymptotic to the finite polynomial. And as long as I stayed relatively close to x equals 0, because that's what it was expanded about, it looked the same. Remember when I went -10 to 10? Didn't look the same. 10 is too far away. But when I kept close. So how many terms do I have to do before I can, go -10 to 10, -100 to 100, -1000 to 1000, and have it look the same? Well, this means you got to do more terms. Whoa. So why is that so cool? Because if I had an integral, let's say involving e, but it was a really complicated integral, I could do the power series instead of the e and integrate that and evaluate it, and I would get a meaningful answer. That's where we're going. That's the whole point of all of this stuff, because you can answer questions that could not otherwise be answered. But this is one of the first coolest results. So this is generally considered the most important power series, because so many things can be done from that particular one. And we're going to derive it. I'm actually going to show you where the derivation came from. I just said, let's take the derivative, and we noticed, hey, we got the same thing back again, which is pretty cool if you think about it. Okay, any questions? Right, this is power series. This is what it is. So we're just now